What if you want to study this ball? Now, if you were in a Calc 3 class, you could say, hey, the equation for this ball is x squared plus y squared plus z squared equals r squared. I know that. Not that interesting. What if we didn't have that luxury, though? What if we didn't have the luxury of seeing the properties of this ball by looking from afar? What if you had to zoom in? What if you were an ant on the surface of this ball? If you were an ant, you can't see the global properties of this ball. All you can see are the local properties. All you can see is what's like directly around you. And to the ant, well, the ball isn't curved. It's obviously flat, right? Because, hey, if you zoom in far enough, it looks flat. Same thing could be said for our Earth. It looks flat if you're close enough. But we know that the Earth is not flat. We can see if we zoom into the ISS, the Earth is obviously not flat. But if you zoom into the Earth, we can see that the Earth is flat. So how do we study the mathematical properties of the Earth? Well, you move. You go from here to here, here to here, here to here, and you slowly traverse around this ball, making a map of what the Earth looks like and what things change as you move from point to point. And slowly, this ant would be able to study and make a map of this entire ball in the 2D plane. Now, this ball is one example of a manifold. A manifold is a topological Hausdorff space that is locally Euclidean, or flat. Now, that's just the technical definition. I have a drawing here of an example of a manifold. Now, you have to put on your abstract glasses and sort of accept the fact that this is an m-dimensional manifold. M-dimensional just means that there are m coordinates. We live in three-dimensional space. There's three coordinates that we use to define space, x, y, and z. This is an m-dimensional space, it takes m dimensions. Now, there are things you can define on this, like a point. We can define curves, we can define vectors, we can define surfaces, and all sorts of different things on an m-dimensional space. Now notice how this m-dimensional space is curved. But how do you study this m-dimensional space? Well, if you're just an ant on the space, you got to do the same thing as this ant did. You got to zoom in. And when you zoom in, it's locally flat. You can see how this curve looks like this, and these vectors look like this. Now, the way you would, study the mathematical properties of this manifold is by moving slowly and slowly. Let's say you traverse this curve and you land at this point. You zoom in here. You can have another map, a map that goes from M to Rm. Now notice how these vectors and this curve looks a little different. Slowly, you can build up the mathematical properties of this manifold by studying how it changes in small areas. Now, we use manifolds everywhere in physics. Our continuous symmetries are Lie groups in physics. The cotangent bundle of Hamiltonian mechanics is a manifold, and possibly the most popular manifold is the four-dimensional spacetime of general relativity. Manifolds are used throughout all of physics, and this is why they're really important to study.